Hello, my name is Yesong Cho, and I'm a student at the Graduate School of Data Science at Korea Advanced Institute of Science and Technology KAIST, and Professor Moon-young Lee is my advisor. On this occasion, I will present our paper, which titled is Deep Learning-Based Defect Detection on Livestock Operation. In this paper, we propose a data-efficient and noise-resilient image-based defect detection model for detecting defect items occurring in the livestock area. We have organized this presentation in the following way. First, we will introduce the problem definition and research question about our work and present related works. Then, we will present the research framework to solve the problem and the results of the experiment. Finally, we will share the contribution of our work and then limitation and future work. Our work can be summarized as shown on this slide. First, we propose a data-efficient and noise-resilient livestock defect detection model, which is efficient to solving real-world anomaly detection problem. Also, we used loss inversion to the reconstruction loss in our autoencoder-based model and an adversarial tech, namely fast gradient sign method, to handle extreme class imbalance in livestock data. By doing so, proposed method outperformed existing anomaly detection models in the real livestock image defect detection task, which has problem in extremely imbalanced data case. Now let's move on to the introduction part. With the development of learning-based models and the emergence of deep learning, many advances have been made in the field of computer vision, which has also contributed greatly to solving various industrial problems. Computer vision is also widely used in the field of detecting defective products from image data taken during production. Computer vision is also widely used in the livestock system, which is often used in terms of managing the welfare of animals in real times. Studies are being conducted to estimate body parameters such as weight and height from animals' images, and studies are also being conducted to detect anomaly behaviors of animals using video data. However, research has not sufficiently been made when it comes to developing a model that detects multiple defects occurring in the actual livestock products. This was due to the presence of three major challenges. First is the lack of data set to perform this task. There are many limitations in developing models because there were not enough data sets to train the model. The second is a data imbalance issue. In the field of defect detection, data imbalance naturally exists, and in the field of livestock, the degree of imbalance is extremely large, making it difficult to simply use a general anomaly detection model. In addition, it is more difficult to develop a model because the image itself data that is difficult to distinguish defect and normal at a glance with the human eye. So we understood that we need to develop a robust model for these data sets that were extremely imbalanced data sets. Now let's discuss about the related work to our research. In agriculture, fruit and vegetable disease detection has been main research subject. For instance, Deng et al. Proposed a deep learning-based automatic carrot grading system. Van et al. Proposed a CNN-based model to detect defective apples. However, livestock has been out of research focus of defect detection. Previous research has focused on body parameter estimation and animal behaviors. Fernandez et al. Evaluate body measurement, shape descriptors, and prediction of body weights in pigs. Jean et al. Proposed is focused on recognizing fattening pigs' enrichment and engagement behaviors. Practically, it is difficult and costly to collect large-scale label anomaly data that the model should learn with a dataset that includes only a few anomaly data labels. Consequently, it is often suggested to use readily accessible label data as much as possible. Also, to maximize the utility of limited anomaly data, the techniques that capture and represent the difference between normal and abnormal have been used in popularity. One of the most popular examples is to set anomaly scores based on one-class classification. Examples for the one-class classification-based model include Deep SVDD and DeepSet proposed by Ruff et al. And DevNet proposed by Pang et al. In Deep SVDD, we train normal data to optimize the model to a representative center in the hyperspace, which is called C. Then in 2019, Ruff et al. Make more progress with their model, which can use anomaly data by adding a loss inversion term to Deep SVDD's loss function. Then, as another training method to use anomalies data, DevNet trains end-to-end learning of anomaly scores by neural deviation learning. However, the aforementioned models are vulnerable to the data noise, and the generated anomaly representation may not be suitable for the dataset with extremely few anomalies. And then to enhance the robustness of model, many researchers try to use adding noise parts of samples. Such techniques are called adversarial attack, presented in the prior research. The fast gradient sign method, which called FGSM, proposed by Goodfellow, is one example. Then many researchers use this adversarial attack to make their model robust to noise. For instance, special model also generate adversarial samples to prevent misclassification system failure in cyber physical production. Gomez et al. Generate adversarial samples by using unique adversarial attack method for intrusion detectors in industrial control system. In summary, the problem of defect detection in livestock was not frequently studied because of lack of dataset and hassle of class imbalance. Many one-class classification methods for detecting defects have been studied, but there are limitations in using labeled anomalies when few defects occur, such as in the field of livestock. In addition, many studies have attempted to apply the adversarial attack technique to develop a robust model for noise in defect detection studies. So, we aim to develop the data efficient and noise resilient model for livestock defect detection problem. Now let's move on to our research framework. In this chapter, we will explain the overall architecture and its components in the model we propose. First, we introduce our framework overview. The proposed model performs autoencoder-based anomaly detection. We use 448 by 448 images as input. However, the target to train with reconstruction loss is not the original input, but based on the future vector that has passed through the convolutional block, which can be any CNN model. Encoder and decoder are composed of two fully connected layers, and batch normalization and the ReLU activated function and dropout were applied. In addition, adversarial training is utilized to aid in reconstruction of latent vector Z. We add a discriminator that helps the encoder learn feature better than the Gaussian noise, which is not distinguishable from normal or anomaly. That is, the encoder serves as a generator of the GAN architecture. In other words, the proposed model is an adversarial autoencoder-based anomaly detection model. Specifically, we added the loss inversion term to the reconstruction error to help better detect anomalies. These allow the autoencoder to learn to reconstruct normal data much more often than it would reconstruct anomaly data. In addition, in order to make a robust model for noise, FGSM was applied to normal data to generate the perturbed normal samples. And by labeling these as anomalies, we performed additional training. Finally, in the decision part, the model selects the most appropriate threshold based on these reconstruction errors. Then let's take a closer look at the components of the model. The convolutional block in the encoder consists of all blocks of the classification head from the CNN model. When the input image passes through the convolutional block, a one-dimensional vector is returned. Then reconstruction is performed on this vector using an autoencoder. The reason we do not reconstruct the original input image is to avoid reconstructing irrelevant or unimportant parts, and most importantly, to reduce the burden of reconstructing the entire input image. To fully exploit the future vector for anomaly detection with the reconstruction method, the future vector should involve discriminative representation that is comparable to the original image. Hence, we adopt the convolutional block from a CNN model to extract useful future information. As a CNN architecture, we use the pre-trained VGG90 model. Then the second part is reconstruction loss inversion in adversarial autoencoder. Through an autoencoder, we attempt to detect anomalies through reconstructed images to better understand normal images. Especially, a variational autoencoder, VAE, is usually used to detect anomalies by creating samples based on the distribution of normal data. When anomaly data is introduced to VAE, it deviates from the learned distribution, resulting in a larger reconstruction error that's used to detect anomalies. This VAE assumed the learned prior distribution as a Gaussian distribution. However, we want to train a noise-resilient model, which is not confused with the unclear samples such as Gaussian noise. This study, therefore, used an adversarial autoencoder rather than a VAE, as it could make our latent future more clearly distinguishable from unclear samples. To better detect confusing anomalies, we not only use a reconstruction error, but also borrow loss inversion concept from the deep set model. In this equation, the second term means the loss inversion. When we reconstruct anomalies future vector, we intentionally make it reconstructed so that it is not similar to the original future vector. And then to make a noise resilient model, we use the adversarial attack method. Especially, we apply FGSM attack to normal data to generate unseen anomalies, which are difficult to predict as normal, and use them for training. This attack can be applied through a simple linear perturbation. In this equation, we generate unseen anomalies by perturbing a sample of normal data, especially using gradient method. When training these samples, the model makes prediction in the direction of increasing loss. Of course, there are other methods to add noise, such as Gaussian noise. However, in the case of Gaussian noise, which is commonly used for attack, two parameters, mu and sigma, must be optimized. However, FGSM can be optimized faster because there's only one parameter, epsilon. In the model training, the attack is applied directly to the input image, and when performing one epoch, the model is trained on the original data and then on the perturbed samples made by FGSM. Now let's see the experiment results. First, we used two datasets in our experiment. First, we used CIFAR 10 as a benchmark dataset. The CIFAR 10 dataset is used to verify the validity of the implement models. By replicating the results from the prior research with a benchmark dataset that includes a relatively high ratio of anomalies, we could first ensure the reliability and validity of the implement models before we test the models against the real-world data with an extremely low number of anomalies. To utilize the CIFAR 10 dataset in the context of a one-class classification-based anomaly detection, two classes were used, and the ratio of normal and anomaly was set to 2:1. And then for the real-world dataset in the livestock, the raw chicken carcass dataset was used, which was collected from the chicken meat processing factory. All the collected carcass images defects were distinguished by the livestock experts at the processing factory. The defective cases were distinguished based on the characteristics related to product grading, such as broken leg, injured skin, and bent wing. The total number of normal data is 30,493, and that of anomaly data is 85, which makes the ratio of 1 to 0.00828. This number of anomaly data is extremely small. And in the below table, we actually oversampled anomaly data as 55 to 1,100. We will discuss the reason behind this later. And then we used two models, DevNet and DeepSet, as comparing models. These models are popular in semi-supervised learning of anomaly detection, which use limited label anomaly data information. Specifically, to train DevNet, we need oversampling, since DevNet focuses on anomaly score, not feature representation, so the power of learning is deemed not enough. So then we did oversampling to anomaly cases. And the first table shows the hyperparameter setting. We set the epoch parameter to 200 times. Model trained 10 times with early stopping. Then we used the batch size as 16 and used SGD as optimizer. The table below shows the best validation error of each model on two different datasets. To assess the performance of our model and the comparison models, AUROC was measured for evaluation. Among the compared models that were trained and tested with CIFAR 10, DeepSet outperformed the other models. However, Our proposed model also showed a relatively high AURC score, so we could assume the proposed model is effective in detecting the defects in the imbalanced dataset. The comparison made with the chicken carcass image dataset showed different results than the prior comparison with Cypher10. In chicken case, our proposed model showed the highest AURC score, which is similar to the performance on Cypher10. However, the performance level deteriorated significantly with DevNet and DeepSet. Especially in the case of DeepSet, the AURC marked only 0.5 in that it predicted all instances normal. This shows that the difference between normal and anomaly data cannot be well distinguished by the traditional one-class classification model in an extremely imbalanced situation. Our proposed model utilized the loss inversion technique and FGSM attacks on the adversarial learning in the end-to-end one-class classification model so as to secure the robustness of the model and produce the superior performance. And next, we did post-hoc analysis of our result. First, to check how loss changed each epoch, we checked the validation error recorded by the model during 10 epoch times. As shown in graph, with Cypher10, DeepSet outperforms the other models during all 10 epochs. On the other hand, our model performs the best when evaluated on the chicken carcass dataset during all 10 epochs. Then, to independently assess the influence of loss inversion and FGSM attack on our proposed model performance, we conducted an ablation study by setting up 3 experimental conditions. First is baseline, in which neither loss inversion nor FGSM were used. Then second, one is loss inversion case, we call LI, in which the loss inversion technique was applied to anomaly cases. And then loss inversion plus FGSM, we called LI plus FGSM, in which the loss inversion technique was applied to anomaly cases and FGSM samples. Then in ablation study, we not only use VGG90, but also another CNN backbone model such as ResNet and DenseNet. As shown in below, compared to the baseline, the performance was noticeably better when loss inversion technique was applied to anomaly cases. When the loss inversion technique was further applied to the data generated by FGSM, the model outperformed the 2 other models, indicating that the data generated by the FGSM attack can serve as unseen anomaly cases. Now, we would like to mention the conclusion and limitation of our study and the future work. First, our research has some limitation. First, we need to evaluate the solution against additional dataset, including various types of anomaly, defect, and product. In other words, the robustness and generalization of the proposed model would be ensured by testing the proposed model using additional dataset. Our ongoing research is considering such issues. Currently, we are trying to apply the study findings to other animals, including pigs and different type of data, including video, as video monitoring of livestock in the natural farming environment is becoming important for smart livestock farming. And then conclusion of our research as follows. This study proposed a deep learning-based anomaly detection method for an extremely imbalanced dataset to livestock quality control. By using FGSM attack and loss inversion, we suggest the data efficient and noise resilient anomaly detection model to extremely imbalanced dataset in livestock. Experiment results showed that the model outperformed in raw chicken carcass dataset with an extremely low portion of defects. So we hope this research will contribute to introducing visual defect detection in the livestock operation with extremely imbalanced dataset. And this figure is our total pseudocode of our model. And thank you for listening our presentation.